Okay, so we keep on going with our lectures in the morning. So the next talk is going to be by LINDSAY from Oak Ridge National Lab. And he's going to talk about phonon thermal transport in 2D materials and 1D and bulk.
I turned it to mute, not on. Okay. Thank you, everyone, for having me. First, I want to give my little gift. So I got a cup for coming here, which is nice. Oh, there you are. Okay. So I like to always bring people invite me somewhere. I like to bring them a cup from Oak Ridge. So here you go, Oak Ridge National Laboratory. I think it says Summit Computer in the back, but I think that might be phasing out after some time. We moved to Frontier or whatever. It was really weird waking up this morning and getting out of the hotel because everyone else was in like bikinis and swimsuits, and I was in my little work gear. So I stuck with the tennis shoes though. So I feel a little bit down dressed, but it's really nice to be here on the beach. My in-laws own a place on the beach, so we like to go vacation there a lot. And so it's kind of fun to come off season and kind of see it, although it's still kind of on season. So I know this is 2D materials, well, combined workshop, 2D materials and spintronics. My problem is I like to stray into 1D and bulk and all kinds of different systems. But I think what makes 2D materials even more interesting is when you compare them to 1D and bulk materials. So hopefully I'll get through some of the bulk material stuff and then move on to the 2D later. I also threw in some pseudo spin stuff. So I don't work on spins, I work on phonons. But we did work on an anti-ferromagnetic semiconductor to try to understand the magnetism in it. And to understand thermal transport in it, so I kind of threw that in there too, just to say, hey, look, I looked at spin stuff. Although we found it wasn't very interesting. We found that the phonons and the spins don't really talk to each other much. Although there's some interesting science coming out from a collaborator of mine, Raphael Herman, who actually says, no, these paramagnons, but we'll talk about that later. Okay, so I'm from Oak Ridge National Laboratory, just like Juan Carlos here. There's not a lot of similarities between his tutorial and this talk, though. I'm a theory guy, he's an experimental guy. But I do want to say I do have aberration-corrected lenses in my glasses. In fact, one time they put a 10-degree, they got it off by 10 degrees, and I kept going, what is wrong? I would turn the glasses, and I could see, and I was like, there's something wrong with this. But anyway, they tell you have to get used to it, but I had to go change it. I don't put all the pretty pictures in there. I wish I did. There was some other similarity I forgot. Oh, we both flew here for a very long time, but okay, so I look at phonons. Specifically, I look at thermal properties, more specifically, thermal conductivity. I usually just gloss over this slide because I'm not interested in motivation. I try to give this to the program managers. Oh, this is why we should be interested. But since this isn't primarily a thermal transport talk or conference, I thought maybe I should throw this slide in there. But thermal conductivity, thermal properties are super important for lots of different things. For one, we have thermal runaway in our batteries. We need to find ways to manage this. Samsung had some issues a while ago. Our CPUs, as they get smaller and smaller and the transistor density gets higher and higher, they tend to get hotter. The power density increases, and so you have to find ways to cool it. So here's a picture of an egg cooking on a CPU. We have all these engines, these turbine engines, that we want to operate more efficiently, and to do that, we want them to operate higher temperatures. However, higher temperatures melts things, breaks things, causes corrosion. So we want to develop different coating technologies that block thermal transport, thermal barrier coatings. So there's a lot of technological issues related to thermal transport and thermal properties. But I like this one the best, although it's getting old now. We have newer versions I should put in here. This is for the US energy economy, where we get our energy. So a lot of it's still from fossil fuels, although biomass somehow got stuck down here, which is a little strange. So a lot comes from fossil fuels, goes through transportation, industrial things, commercial processes. And at the end, we get about 67% of it's just rejected as waste heat. So we want to find ways to make it more efficient along the line and try to capture some of this back. And so one interesting type of material, it's called a thermoelectric material, you can use to take a temperature gradient and convert it back into electrical energy. Although we haven't got materials enough that are efficient to actually make it commercially viable, it's still used in some applications like satellites, which are going off to explore the universe. So that's kind of like the motivation. You can read that up there if you want. I'm more interested in the science. That's what I like. So I kind of gloss over that, let the program managers see it. And this is my science, basically. I used to use interatomic or empirical potentials to describe the way atoms interact. I think that's how you know me, maybe. But over the past 7 years or so, I've switched to using more density functional theory approaches to describe the atoms. Mostly because you can kind of trust their accuracy a little bit more. But really for me, it was because with each empirical potential, I was kind of stuck with a material. And then I would have to go, when I wanted to look at another material, like gallium nitride in my case, if I use the same empirical potential, the parameters weren't all quite right for phonons. They were all developed for like structural properties. So I switched to DFT because then I wouldn't have to change all the parameters for each material I want to look at, and I could kind of trust some of the results. Although DFT has problems as well. That's kind of the workforce. That's what describes my interatomic forces. And what I do is I take derivatives of those interatomic forces to get at the vibrational properties of a system. And then if I take the third order derivative, sometimes fourth order, I can get at the thermal transport properties of a material. So let's just start the easiest, the second order derivative of the interatomic potential here. We use to construct this thing called the dynamical matrix, which describes phonons, or the normal modes of vibration in a crystal system. And that's where some of the challenges are coming lately, is that a lot of the systems we want to look at aren't quite crystalline. They have defects, they're amorphous, all kinds of mess. And so some of this won't work. But so for now, we're just going to focus on crystals and then how we might work into the future to look at other materials. So you take these interatomic force constants, these harmonic force constants, you build a dynamical matrix as a function of masses. This will show up later. And then you diagonalize this matrix, and you get a set of frequencies with different polarizations, different ways that the atoms can oscillate and vibrate. And so this is what we call a phonon dispersion, where we've just diagonalized this for different points in the Brillouin zone of a crystal. And this is hexagonal boron nitride. So the curves are my DFT calculated results. And the black circles are from, I think, inelastic X-ray scattering in this case, but it may be neutrons too, I don't know. We love neutrons at Oak Ridge. The group I work with, they used to love X-rays too, but then all the managers said, no, you gotta look at just neutrons, and so it's been kind of a struggle for the past couple of years. But you can see that we get very good agreement with the measured data. So if you look at different kinds of potentials, you'll find things will be way off for like the optic modes, or you'll miss for some of these acoustic modes. So I guess I want to point out, it's these modes here, these highly dispersive modes here that really we've always thought to carry the heat in a system. Because these phonons here are really fast. If you take the derivative, that gives you the velocity of the phonon, and so they're really fast, they can carry a lot of heat. These modes up here were often neglected, these optic modes, optic because they can be optically excited, so that's a Raman data point. But they're important because these guys can interact with the acoustic modes to scatter them, to limit their phonon lifetimes. So those can be important too, and so that's something I've discussed over my career in all these papers. Okay, so harmonic force constants give me phonons, but phonons have infinite thermal conductivity if you just think of it as a harmonic level or without defects in a crystal. You need to introduce anharmonicity or phonon-phonon interactions in order to limit the thermal conductivity intrinsically. So then you have to take the third order derivative, which gets kind of messy. I just put V3 up there and you just show pictures of the third order derivative here, so these interactions. And so there I had to do a lot of work, making sure that I use all the symmetries I can in the crystal, mapping all the symmetries to reduce the number of calculations. I think I used to have a slide that said, for gallium arsenide, if I went to 5 nearest neighbor interactions, I'd have to do like, 600 million, well, no, it's 5 million CPU hours just for one calculation. But using symmetry, you can boil that down to about 5,000 CPU hours, so it's kind of nice. So I spent a lot of time, a couple of years doing that so that I could do all these fun things I'm going to talk about later. So once I have these harmonic force constants and these interatomic interactions, what I do is I just simply use Fermi's golden rule, quantum perturbation theory. So I have this set of phonons here. I sandwich them between my anharmonic perturbation. And then I just calculate a scattering rate as I sum over all the possible interactions for a phonon Q with Q prime and Q double prime. So that's the sum over here. So that's part of a lot of the work I do is just finding all these interactions. And hopefully I have a slide later that talks about phase space and how that's important. Once I find those, though, that doesn't give me the thermal conductivity. In the relaxation time approximation, where you assume all the other phonons are in equilibrium, it'll give me a lifetime. But oftentimes, like in high thermal conductivity materials, like in lithium fluoride at 10 Kelvin, that won't be a very good picture. You actually have to go and solve this thing called the Boltzmann transport equation. So that doesn't assume that all your phonons are in equilibrium. It assumes they're all in some non-equilibrium state. And then we solve this equation, this Boltzmann transport equation. So I think I put Piles up there and Boltzmann there. Piles is the first one that applied the Boltzmann equation for gases to phonons. The reason I have to do that is because my old advisor at the Naval Research Lab, he was Thomas Reinecke. He actually worked under Piles for a while, and he's like, look, man, you got to say Piles-Boltzmann. I'm like, okay, I'll do it. So when I solved this Piles-Boltzmann transfer equation, so I got this is just velocity dotted with the temperature gradient. You have this non-equilibrium distribution of phonons changing with this temperature, and then you have these non-equilibrium distribution phonon changing in time due to the collisions. I solved this in a steady state in the linear approximation. There's a lot of details. If you're interested, we can talk later, but not here, that go into that. When I solve that, I get these non-equilibrium distributions. I then convert those into a lifetime, and you don't necessarily have to convert it to a lifetime. It just helps you intuitively understand what's going on. And I use them in this equation here. So this is the thermal conductivity. It's just a sum over all phonons that can carry heat or don't carry heat. You can put them all in. This is a specific heat. This is their velocity, so it goes as squared, so it's important to have fast phonons if you want high thermal conductivity. And it's a function of their lifetime. And it's that lifetime that's really hard to get at. But once you do this mess, you can actually start, especially when you use DFT, you can start making predictions of material properties. And so here's just one where I did the thermal conductivity of lithium fluoride as a function of temperature. And I looked at different lithium concentrations. So there's a lot of experimental data out there. Yes and no. So if you have a really low thermal conductivity material, they're equivalent. It's just going to be like the full width half max. Okay? For like a high thermal conductivity material, you actually have to go solve this equation. We call it a transport lifetime. So it actually needs a temperature gradient in order to determine it. Experimentally, they can't yet. So I have an experiment that I'm trying to get going on boron arsenide, which I'll talk about later, which is a high thermal conductivity material. They can do it on very low thermal conductivity materials. They just say full width half max. But what I'm trying to do is get a really nice sample of boron arsenide. The problem is you have to have isotopically pure boron-11 to shoot neutrons at it, because the boron likes to accept, boron-10 likes to suck them up. And you have to have really good samples for neutron scattering measurements. So that's a challenge, is developing really good samples of this boron arsenide. I think you're talking about sample prep and stuff. And then we're trying to put it in a neutron beam and use these special Lamar precession techniques to get at the resolution. So neutrons have a pretty big resolution. I think it's 2 MeV. Is that about it? 1 or 2 MeV resolution, which for materials like boron arsenide isn't good enough to actually look at the lifetimes. Your instrumental resolution is bigger or as big as the lifetimes of the phonon, or the lifetimes of phonons are much smaller than the resolution. So they have this technique that can bring that down an order of magnitude. So we're trying to do an experiment to. But the next thing I want to do, though, is then put a temperature gradient across it in situ. So I don't know whether we'll see these changes or not. But anyway, so the process is phonons, scatter phonons, sum them all up, solve the Boltzmann transport equation, get thermal conductivity, compare with measurements, or make predictions. So in this case, we compare with measurements. It worked pretty good. So this is all different isotope concentrations. So I can also do the same sort of thing with phonon isotope scattering. And I'm going to talk some about phonon defect scattering as well later on. But first, I kind of want to show that it works not just for lithium fluoride, but for a whole different number of systems. So here's where we looked at MgS2, Mg2Si, and then we looked at different alloys of it. So there's a lot of experimental data for that. So we fit the data pretty well. Here, it's kind of questionable whether that actually works. But we won't talk about that right now. Here are some of the first calculations. We're in germanium silicon, both isotopically pure and for naturally occurring isotopes in the system. Again, you get very good agreement with the data. Here's more high thermal conductivity. I looked at aluminum nitride, silicon carbide. So here are the curves, hitting the data pretty well, except at low temperature. At lower temperatures, it's impurities and defects and boundaries that tend to start playing a bigger and bigger role. So it's not surprising when our calculations over predict the thermal conductivity at low temperature. But these are the things that we wrestle with when we're trying to compare. And then one work I really liked was thermal conductivity versus temperature for gallium nitride. So again, we found reasonable agreement with the experimentally measured data, at least the highest measured data by SLAC. However, if you can isotopically enrich the gallium atom, you can actually get a pretty big enhancement in the thermal conductivity, which is important because gallium nitride is one of those high-power electronics devices that the Navy likes to use, at least the US Navy anyway. And so it's important to try, as these high-power devices operate, they get really hot, and so you want to try to carry heat away. So if your intrinsic material can carry heat pretty well, then that's good. The problem is gallium's not that easy to isotopically enrich. They do it. And I think someone has done it, maybe with Gang Chen's group, and they have not verified that, though. They've only seen about a 15% enhancement. So we'll see. So nitrogen, actually, the isotopic concentration of N14, I forget which way it goes, it's 99% pure, or maybe 99.9%, and so it's okay. Even if I take those out or enrich it, it doesn't do anything. It's the gallium, yeah. Another thing is the heavy atom. When you have these compound systems, the heavy atom governs those acoustic phonons that I showed on the other slide. So the heavier atom governs these vibrations here, and then the light atoms governs these high vibrations there. Because the lighter the mass is, the higher the frequency is going to end up being. The lower the mass is, the lower the frequency. And so if it's those acoustic modes governing the heat transport in the system, whoops, wrong way. And it's really the gallium that's going to be more important for gallium nitride. So anyway. Channels. Right. So they will interact, and I think that can somehow show up in the iteration scheme, but through 3 phonon anharmonic matrix elements, in my terms. Yes.
Sorry. So. Oh. This is loud. So, my question is, the acoustic and optical phonons will interact.
So it's acoustic and say 2 optics, right?
Yeah, and then how do you know, for instance, from the dispersion that you have in there, when they will interact? Can you do it visually? I have no idea. That's what I'm asking.
Okay. So I may have slides that go to that, but I may not. So I'll gloss over those slides when I get to them. But what we do is each one of these interactions has to conserve momentum, crystal momentum specifically, and they have to conserve energy. So what I do is I pick a phonon, say right here, and then I do an integration over all the Brillouin zone, looking at all phonons number 2, and then I search to find phonon number 3 that satisfies conservation and conservation of energy and conservation of momentum. So that's what I was talking about earlier when this sum here is most of my time is spent there just searching for these processes that can solve that. Okay? So I'll find in this hexagonal boron nitride, I'll find 800 million processes or 800 billion on whatever grid I had. And then once I find all those, I sandwich that matrix element in there, calculate its little lifetime or its scattering rate at that RTA level, and put it in this equation. Now, much of the time that phase space governs whether phonons can actually interact. So for instance, this optic mode way up here, if you have 2 acoustic modes here, they'll never have enough energy to interact with that guy. So we've developed some intuition about looking at the band structure, what kinds of band structures give you high thermal conductivity, what gives you low. And that's what I have on another couple of slides, I think. But that's what we do. Does that answer the question?
Yes, it actually answers the question. We should work together, actually. It's interesting.
I know, I'm getting kind of interested because you can actually look at vibrational properties now, right? Okay. I did work with the MaxStem one time looking at boron arsenide anti-site defects, but it didn't match my theory, so I don't put it up here. It never quite does. It does. I don't know. So anyway, I like this method because it's shown quantitative accuracy, although I want to put a caveat in here. These are really nice crystals. You'll find that the crystal's really messy, lots of defects. It's not going to work. And then there's other things you have to do and try to understand. what else I want to say? What I really like about it is flexible and transferable. Like I can actually take two different elements on the periodic table, I can put them together and say, okay, I can calculate thermal conductivity. We'll see what happens. Sometimes those materials don't even exist, and then you call it a prediction. So I want to talk about, after this, I want to discuss 3 bulk materials. I'll try to go quickly so we can get to the nano stuff, to kind of walk through some of these things that we were just talking about here. And the next one is really just to say I did work on a system that had spins in it. So I thought I would just mention it. So this is an anti-ferromagnetic semiconductor called manganese telluride. I think a paper just came out 2 weeks ago in Science Advances, not with me, but with this guy, Herman, who looked at paramagnons and paramagnon phonon or electron drag. And so they found that they got a very large Seebeck coefficient because the paramagnons were kind of dragging the electrons along even above the nail transition temperature. So they found that kind of interesting. They use their neutrons to kind of measure these things. But for me, I was just interested in the intrinsic thermal properties and vibrational properties and the sorts of things that can happen. So we had a postdoc who was very smart who did all the magnetic structure calculations. And he did a really nice job and kind of refined these J parameters for a Heisenberg model. I didn't quite understand all that. I'm a Phonon guy, right? But I learned quite a bit as I was going through this process. And we worked with a guy named Randy Fishman who does magnon modeling and not transport per se, but looking at the dispersion. And so here we have the calculated dispersion that we get, this blue curve, but that's for a 300K structure. And there's only one data point at 300K at this point here, and it is reasonable. We should have tried to fit this data too, but there was something strange about it. So that's the magnetic stuff. We did pretty good at calculating the nail temperature when we did a pair cluster expansion. Mean field theory doesn't quite work there. But again, I was interested in the vibrational properties and thermal transport. And so we looked at this system and we tried to kind of guess certain things. Like for one, it's an anti-ferromagnetic semiconductor below the nail transition temperature, and then it goes paramagnetic above the nail temperature. But the thought is that if you can sandwich if you look at the ferromagnetic state and the anti-ferromagnetic state and calculate the phonons for those two different states, if they're the same, then they're probably not interacting with the spins very much, right? They're not, affected by it. And that's what we saw. We were kind of hoping to see big differences, because then we could say, oh, there must be spin-phonon coupling, and then I'd say, well, I don't know how to do that. But what we did find was there's not very big differences, especially for these acoustic modes. It was nice that we fit the experimental data, so the black circles and neutron data in the system, not our own. Here is our own neutron data, but we only had powder samples, so we can only do the density of states. And yeah, the features are okay. I was a little unhappy, but then I learned a lot about how they fit these things and do stuff. So I got a little nervous about that. But I was more interested in, again, the thermal conductivity. So this is lattice thermal conductivity versus temperature, both for the ferromagnetic state, anti-ferromagnetic state. It's anisotropic. So on this, yeah.
Sorry, can I ask a question? So dots are the experimental results, is it?
Dots are experimental always, yes. Yeah. So sorry, dots are experimental, and then the curves are my calculations or the postdoc's calculations. Sometimes we flip back and forth. And then we could actually project, because we did 2 different measurements, so they could project onto the tellurium atom or the manganese atom. Yes. Oh, this is 300K. Yeah. Actually, the black is 300K. The red, is it red? The blue was about 40K, but they temperature corrected. That's where I start getting like a little nervous about experimental results sometimes. Like, wait, you just temperature corrected? What is this? My data is 300K, though. I can say that with precision. And then we have, lattice thermal conductivity versus temperature versus some of the available experimental data here. It seems to match the in-plane. The problem is I couldn't get much information about the structure. These are polycrystalline samples, so they should have lower conductivity than we see. But also it's for thermoelectric, so I imagine they just did whatever they could to mess the thermal conductivity up. So really, I guess you would actually supposed to see an average of these, which would end up in here. So anyway, that agreement there is maybe a little bit artificial is what I'm trying to say. It's like our number, the average should be in here. Their number is probably not what a real perfect crystal of manganese telluride looks like. But anyway, that was just my spin talk. I didn't even want to talk about that here. But I'm more interested in this material, boron arsenide, because we're still doing experiments on it. and because I think it's what got me a job and keeps me employed. But it's a material that we started looking at for a completely different reason, so I'll tell a little story about it. So this is thermal conductivity versus temperature. Diamond has been known to have the highest bulk thermal conductivity of all materials. Graphene, you might say, is a little higher, although it's 2D, and so I don't know what we're going to do with it in terms of transporting heat, but maybe we can. But it's way higher than all these other materials that people use in their devices and things. It's higher than silicon carbide, about 500. I think copper's used as a heat sink device, and maybe in that laptop. I know my last laptop it was. It's around 230. So diamond's way higher, and it's always been higher, and people kind of know why. It's because the carbon atoms are really strongly bound, covalently bonded. So the tighter the bonds, the quicker they can vibrate, so the faster the phonons are, so the steeper that phonon dispersion. And the optic modes are really high up, so they're not interacting with the acoustic modes very much. And they're very light atoms, so they're tightly bound light atoms, so they can oscillate very quickly, and you can get very fast phonons. Silicon has a higher or heavier atom in it, and the bonding is a little less strong, and so that leads to a large discrepancy, a large drop in the thermal conductivity compared to diamond. So we were interested in gallium nitride previously in terms of its isotope effect, and so we're like, oh, what other materials can have a really strong isotope effect? And we said, oh, wait, what if we switch these two? Then you have boron arsenide. So if you look at the periodic table, go across that row 4 element, it's just boron arsenide. So we toss that into the computer, and this is what we got. We got thermal conductivity that's about the same as diamond, even though the masses of the arsenic atoms are way heavier. And it was even higher than diamond, at higher temperatures. And so I did this calculation, I don't know how many years ago, and I ran away from it. And I said, this is stupid, and I went and worked on other things. But it bothered me, so I kept going back. So we did other calculations, GGA, LDA, special pseudo potentials for your DFT. I don't think we tried any empirical potentials, although I may have tried a Tursoff or something model. We even had some other group calculate it. And it was within about 10%, they were all the same. And so you start to get some trust in it. And it's really weird when you look at the phonon dispersion. So here's a dispersion of silicon, boron arsenide, and diamond. So we know silicon has a lower thermal conductivity than diamond, about an order of magnitude. And then we know this, well, we can imagine why it is, because the velocity of the acoustic phonons is so much smaller, right? This is really fast phonons. But boron arsenide is similar velocity phonons of silicon, so you think, okay, why doesn't it have a thermal conductivity comparable to silicon rather than diamond? No, it's up here. And what we've reasoned out after a lot of testing and struggling is a couple of things. It's coming from the lifetime of the phonons, not necessarily the velocity. So you notice in that thermal transport equation, you have the specific heat times velocity squared times the lifetime. And so what happens in boron arsenide is that since the mass difference is there's such a big difference between the masses of these atoms, the optic modes are very high frequency, and they're governed by the boron. Okay, and these acoustic modes tend to have squished down frequencies because it's a heavy atom governed by the arsenic atoms. And so what happens is you have two acoustic phonons in this material. They can't interact with the optic phonons. So what I call AAO coupling is gone. It's zero. There might be a residual somewhere, but not along this high symmetry direction anyway. And so that's interesting enough, but the same thing happens kind of in gallium nitride. So why isn't gallium nitride thermal conductivity higher? What we found too is that it's also a result of these branches here are squished together. So if you look at silicon, the frequency difference here is much larger than the frequency difference here. And what that does is it eliminates, well, it doesn't eliminate, it reduces the coupling of three acoustic phonons with each other, which I found quite interesting. It took a long time for us to come up with this. What's weird is if you consider just one single acoustic branch, say we just had one, and it was degenerate, and it was just straight like this, then you could always satisfy conservation of momentum and conservation of energy, because it's a linear branch. But anytime you had just a little bit of dispersion, then you can never satisfy it, okay? And so that's sort of what's being approximated here. We have dispersive branches, and we're kind of squishing them onto each other. And so that limits the amount of scattering that these guys can have with each other. And another important thing I found out years after the paper, because I started looking at all these rock salt materials, I'm like, why don't they have high thermal conductivity? And the reason there is the bandwidth of the optic phonons is also important. So if I have a bandwidth, say that frequency range there, then they can interact with phonons of this frequency range here. Okay? And so one acoustic phonon can scatter with two of those optic phonons, but this whole region here, they still can't have AOO coupling. And so we found that all these things put together limited the lifetimes of these phonons. No, increased the lifetimes, limited the scattering of the phonons, and led to a high thermal conductivity. So that was prediction. So we throw it out there. We get rejected by every paper. You know, you go down the line, science, nature, nature materials, nature physics. I think it finally got in PRL. I think it's down there. So we throw it out there, and then people say, okay, well, that's kind of interesting. Maybe we'll grow it. So this is the first time I actually got people interested in growing something. And so these are some of the first efforts. I think Zhifeng Ren, there was Li Shi in there. David Cahill is measuring stuff. So this is Zhifeng's little, no, this is Li Shi's. Zhifeng's, I think he got up to there too. So they started getting better and better samples. They started looking at this thing. At Oak Ridge, we got some samples too, and we used X-ray scattering rather than neutrons to measure dispersion. So previously, there were only those green dots up there. And so that's Raman data. And that gives you some information about the optic modes. Like, oh, the optic modes are fitting, but it doesn't give us any information about the gap or whether these branches are closely packed. So it was really nice getting this data to confirm that at least at the harmonic level, we're getting things okay. So that was some nice stuff. We confirmed that. But the problem is when they did thermal transport measurements, they were getting an order of magnitude lower, about 200 watts per Kelvin. And even worse than that, Glenn Slack, he was a great experimental guy, he had a theory that described boron arsenide and predicted it to be about 200. So I was like, oh, Glenn Slack must be right. There's even a story I heard where he was talking with a fellow that I've worked with, Jerry Mahan, in his office, and Jerry's like, what do you think about this boron arsenide? He's like, oh, it's bullshit. These are the types of things I shouldn't be saying on the camera, but okay. So anyway, so we hypothesized, oh, it must be defects, right? That's what we always do as theorists when we can't get what we want. What we found, though, a year or two later, was that it's not just defects, it's the theory itself. So I found this guy named Julien Rouen, I think I reviewed a paper he had where he's doing 4-phonon scattering, and I got super excited because I was like, wait a minute, if 3-phonon scattering is so weak, then maybe 4-phonon scattering becomes important in a material with 3-phonon scattering is weak. So I talked to him, and I said, I'll get you force constants if you can run the calculation, because I'd done this before, and then I realized I had a bug in my code. I could have done the 4-phonon like 10 years ago, but oh well. It doesn't matter. It's good to let other people do stuff too. I can't do everything. Just kidding. So anyway, I got in the 4th order force constants. He got me the relaxation times. I put them on my Boltzmann transport approach, and we calculated thermal conductivity. And this is what we got. So the green curves are when we did diamond. The black curves are silicon, and the red curves are boron arsenide. At high temperature, you expect higher order processes to become more and more important. And that's what you see. So here the curves kind of coincide with the experimental data here. But at high temperatures, they start to diverge a little bit. And you see that the 4th order scattering kind of describes this 4th and 3rd order together. Describes silicon nicely, describes diamond nicely. We didn't have data for boron arsenide, but you'll see there's a big difference there. Even at room temperature, I think it drops it from about 2,300 watts per Kelvin to about 1,420, which, okay, it's still high, but it's not as high as diamond. It's not as exciting. People are still interested, so they're still growing it. And so finally, I think last year, or maybe a year and a half ago now, 3 science papers came out back to back to back, kind of funny. I guess 2 of them kind of worked together and 1 didn't. So it's kind of funny that they all got together. But it kind of verified this result. And so I think each of them got over 1,000. And this paper here got about 1,300 watts per Kelvin at room temperature. And so it was really nice for me to finally have something validated. So it's thermal conductivity temperature. This is the experiment of the red dots here. And then the 3-phonon, 4-phonon scattering is here. And it kind of matches pretty nicely. The 3-phonon's still too high. Oh, that's what defects. No, 3-phonon's even up here. So it was kind of over-predicting. It was kind of funny, so I went to visit the guy, Yongji Hu, at UCLA, who was doing these measurements. He was growing the crystals and doing the measurements. So he'd grow a crystal, he'd get about 300 watts per Kelvin. So he said, student, go back. Grow another crystal, get about 400, 500, 600. They kept growing crystals and doing a better job of their synthesis process until they got stuck at about 1400 watts per Kelvin. They're like, okay, keep going back. And they keep having this guy try to break it, but they're at this window, or at this ceiling where they couldn't get higher. And then he saw the paper with the 4 phonon. He's like, oh. And so that's where it's dangerous sometimes to trust what we do. So be careful. Don't send the student back into the lab to grow another crystal when he doesn't have to. Huh? Was I?
Are you in one of those science
No,
papers?
I am not. There's something political here that I won't put on the camera. We can talk about it later. David Broida, my old advisor, he is on one of those science papers, but that's okay. I'm fine. Because the week before this, I got my own science paper, and so I was like, okay. Although this is more of a failure than it was a success, so I guess that's why I put that up there. And like your talk, I like to put an old German paper in here, Elementär Betrachtungen über die thermische Bewegung in festen Körpern by Einstein. My grandma would just, she'd be so upset. She was German, and so she's like, why can't you talk? Anyway, it says elementary observation of thermal molecular motion in solids. So I started working on this material called thallium-3 vanadium selenium-4. So it's a cubic structure, 8-atom unit cell. Yeah, 8 atoms. The postdoc is very interested in it. I wasn't all that interested for a while. I was like, hey, when your units still get so big, I'm like, it's too hard for me. I'm staying away. But it got me thinking about stuff and these lower thermal conductivity limits and things like that. And it got me interested in this Einstein paper where he had a prediction for the thermal conductivity of potassium chloride. And he was off by a factor of 22, which in our kind of field is pretty bad. I mean, maybe not back then, I don't know. But anyway, he thought it was a failure too. And so here's some measured data, and here's Einstein's prediction. And it's because, he didn't have the idea of the phonon yet. Debye is coming along, and they're all kind of working around in these things. And then we found that, when you use a phonon picture, it works reasonably well, although it's you always have to be careful with log scales, right? Like, if I actually, didn't use a log scale, these differences might be a little bit more clear. So anyway, Einstein failed, so I thought I'd put my failure up here too. It's this thallium-3 vanadium selenium-4. And so Einstein's picture of thermal transport is that you have this like vibrational motion of this atom, and somehow it's coupled to say this atom over here. You have this vibrational motion, and that energy will hop to here. And then it'll hop over to here, and it'll hop over to here. And if you drive a thermal gradient, that energy hopping will kind of be, dispersed along. The problem is it predicts the thermal conductivity way too low because these atoms are actually correlated. There's phonons in here. There's wave packets. But nevertheless, people use Einstein's theory in his model to kind of give a lower limit to thermal conductivity in materials. And so here was this system, TL3 VSE4, where we did thermal conductivity versus temperature. We have a guy named Brian Sales. He does a lot of superconductivity stuff. He was big in thermoelectrics, but he loves thallium systems. So when our postdoc found this thallium system with a low thermal conductivity, it was easy to convince him to grow it so we could actually do measurements. So the green are measured thermal conductivity data, and the red is when we use our DFT phonon picture. And the problem here is that we can kind of do a decent job at low temperature, but at higher temperatures, ours goes as 1 over T, which is typical. Okay. Oh, okay. Ours goes as 1 over T, theirs goes as T to the minus 0.6, which, so different temperature-dependent behavior, and also room temperature, we're off by quite a bit, off by a factor of 2. And so to me, that was a failure. I was like, okay, our phonon picture isn't working for this material. I don't know. It's still interesting enough to try to go write a paper and publish, although to me, because if you look at like really low thermal conductivity crystals, these are crystalline systems, it's one of the lowest, so it's way down here. And these ones down here are really weird things. Like, this is gadolinium-117. What am I supposed to do with that? And so I was kind of excited that we had this simple cubic system, but it kind of bothered me that it was so low. And so you look at like the lower thermal conductivity limits, the Cahill-Watson-Pole model. Here's the Einstein, when I use his equation, kind of does this. And when I was looking at this, I started going, what if I just added those two things? And what I found, well, maybe I should wait a second. Maybe I'll jump ahead. What I found is when you add it, if you pick the right parameter, which I don't like to do, you can actually fit the data really nicely. But the thing is, we had experimental data, so we could actually kind of choose a parameter based on the experimental data. For the Einstein model, we get kind of down here, we kind of underpredict. Then for this Cahill-Watson-Pole model, we kind of overpredict, but it kind of gets us closer. And to me, that was so unsatisfying because I couldn't, I like to try to hit the data, sort of. Although I do like getting the physics out more, and so we went ahead and published anyway. Did you want to go ahead with the question, or okay?
I think now it's time for my question.
Okay.
Okay, so Einstein's model is uncorrelated.
Correct.
Okay, your model is completely correlated.
Correct.
What's the correlation length? And you talked before about the lifetime. Okay, so this is related to the mean free path or to the correlation length? When you translate this from time to space.
Right, so yeah, we have to have, like for instance, the size of the crystal should be larger than the mean free paths of the phonons. Otherwise, you should have a boundary term in there that kind of truncates them. For me, for my calculations.
But this is different from the correlation length.
Okay.
The coherence length of the vibrations. This is not the size of the crystal.
Right, so I guess the correlation length then is whatever scattering I put in there that limits it, right? And then you can correlate that to the mean free path. You put that time times its velocity gives you the mean free path of the phonon.
Okay,
so they all have different mean free paths. So here's a function of mean free paths for a bunch of different frequency phonons, right? So I have a whole bunch of different, so acoustic phonons are really large mean free paths. I hesitate to say correlation length. Usually when I think correlation, I have two phonons that are correlated. They know each other, and so
yeah, they are in phase.
Right, in phase.
They're vibrating in phase. So, but this is what is missing in the Einstein's model, or the mean free path? Well, I mean, your phonons
first
are
off, Einstein's
completely
model
correlated all are around the crystal. Is that correct?
Right.
In your calculations.
My calculation assumes that it's bulk. There's no.
But they are completely correlated all around the crystal. It's the other way around the Einstein's model.
Correlated in the crystal, yes. Not the phonons.
They don't have phase
phonons,
match?
The phase don't, I mean, they have whatever phase they have, yeah. E to the IQR.
But then I don't understand what's the difference with the Einstein's model, because the only difference I see is that they are not correlated in phase.
Okay, Einstein's model, I had it up here too, and I took it down. It's just a guess at how the atom here is, how often this guy wiggles and how often it'll jump to that. It's
not a matter of phase. This is not just a matter of phase, vibration phase.
No.
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 Okay.
So I don't think I'm going to get it. So I'm sorry.
Okay.
But it brings up an important point. Is like, so if I try to add these two models together, this phonon picture and this hopping picture, the problem is they're both vibrational, right? And so if you look at like the specific heat or the entropy of those, they come from the same stuff, right? And so that's where we wrestled with these reviewers, for a while. It's like, well, you can't just add them because then, you're taking energy from one and putting it in the other. And so we said, okay, we'll take the energy out of the phonon systems. Basically, we looked at the Afi-Regel limit. So we said, if we look at the inner lattice spacing, that's, one energy can hop to the next atom. We take all those phonons with a mean free path less than that. They're really ill-defined anyway, right? Because, you can't really define it over like half of an oscillation of the atoms. So we'll take all those, we'll take that energy, we'll throw that away, take it out of the phonon picture. But these guys are still allowed to transport heat. And then those, we'll put that energy in the Einstein picture and then kind of add the two up. And so that was kind of our argument. Honestly, I hated it. I hated this paper. It drove me nuts because I'm like, this is just, there's nothing microscopic in that. And so I like about the paper, though, now that it went out, people started thinking about it more, like, oh, like a two. And I found later, people are already sort of thinking that way anyway. And so now there's a really nice paper by Marzari's group, Simoncelli, where they actually used some of Phil Allen's old work, where he looked at just disordered systems and these off-diagonal elements. So the diagonal will be like your phonons, and off-diagonal is like couplings. When you have band crossings, it can actually mix. But in a perfect crystal, you only have a very finite amount of these band crossings. But in a disordered material, it's like just a mix and match. It's just a whole bunch of bands all mixed together. And so he used that picture. But then Marzari, when it came along and said, well, look, in these low conductivity crystals where, the mean free or the full width half max of the phonons is so large, then even here you can have these crossings all over the place. And so he has a really nice paper that's out. I should have put it up here, but you could talk to me after and I can point you to it. But that's what I'm going to start doing in the future as soon as I code it up and start looking at it. But again, I'm a high thermal conductivity guy. That stuff I don't know. Anyway, you're welcome. So I have 16 minutes left. Okay. Too long. Switching to nano. Here we go. So quickly. I put this slide in here because it's a paper that I wrote and I'll never publish, so I'll just talk about it. The reason I don't publish is because we've hit certain theoretical limitations in my time, and so I can't quite finish it, so we'll see what happens. But I think it's helpful for students and people who are trying to do two-dimensional materials or calculate phonons. So when you calculate phonons, you diagonalize this dynamical matrix, and these force constants you use as input, they have some numerical error on them. And so what we do is when we draw out the raw force constants, we apply certain invariance constraints. So if you use a code, you're always going to apply these acoustic sum rules in some way or another. Usually it's just a simple acoustic sum rule where you add them up, and you take one term out, and you set it equal to the negative of the add, and then that lets you get your phonons to 0. So it's like a translation, forces translational invariance. But there's other important rules, like you have to have point group symmetry, shouldn't be violated in these materials. And so when you do a calculation, there's always some error in there. So what we do is we've developed codes where we look at where these things are violated, and we try to change each force constant as small as possible in order to satisfy these physical constraints, which can be important. So derivative permutation, acoustic sum rules, point group symmetry, people do this all the time. What we find is important for 2D and 1D materials is you also have to satisfy rotational invariance. And there's these things called these Boron-Huang equilibrium conditions. That's here. So Boron-Huang equilibrium says that if you have a system without strain and equilibrium, it has to satisfy these equations. And then the rotational invariance is that equation up there. And so what happens for me, not for a lot of people who publish, the problem is you never see people's mistakes when they publish. You only see like the good stuff. What happens for me is when I take like graphene or hexagonal boron nitride or silicene or whatever 2D material I want to look at, and I do a calculation and I look at the phonons, this is what I get. So I'm zooming in really close to the Brillouin zone, okay? This is very low frequency. We're at 0.3 terahertz, okay? So it's not a huge discrepancy, but it can be important sometimes for phonons. And what I find is that my out-of-plane vibration, which looks like that, so I'm going to tell you that that's a very important vibration for me in these 2D materials. My out-of-plane vibration is supposed to be quadratic going to the zone center, but sometimes I find that it goes imaginary, which, be careful. You don't want to mess with imaginary phonons because they're not real. So all these solid curves are my errors, my problems, before I enforce rotational invariance and Boron-Huang. Notice I have enforced translational invariance, but it's still, the problem doesn't go away. And sometimes I find that it's too linear. Like I get more linear than I do quadratic. And so I guess what I want to say is be careful when you do a phonon calculation. If you want to fix this problem that you're having, you can always go to bigger and bigger supercells. That tends to help, although I found in some cases it doesn't. So over here, I went from an 8th nearest neighbor cell, or 5th nearest neighbor, I got a big thing. 8th nearest neighbor, I got a little bit better. 13, I got pretty close. I was like, whoa, it's all real. Then I went to 16 nearest neighbor. It didn't work again. It drove me nuts. But what I find that always works is when I apply these two conditions to my force constants, I get beautiful quadratic dispersion, and it goes to here. Now, really low frequencies, sometimes I still have issues. But I think that's just a numerical issue diagonalized in the matrix. Oh, run!
Oh, you're not going to...
Oh, yeah, I guess I could do that.
Just the question was, what happened with quasicrystals then, for instance? You will have a quasicrystal, then those things will not apply. Some of these, the rotational invariance.
Oh, so I don't look at quasicrystals.
Oh, that is it.
That's easy enough. I did talk to a guy, and we did have some discussion. I was like, I don't know. I actually even try to look at incommensurability, like these Moiré patterns, and that's almost impossible for me. It's,
Hi. So my DFT collaborators always say that whenever we get a negative frequency, that means some instability. So should I tell them that maybe that's not always the case?
You should tell them it's not always the case. I do get annoyed sometimes when, especially I work with a lot of ferroelectrics guys, and they want to see the negative imaginary phonons. I'm like, well, what am I supposed to do with that? I can't. I would say that if it's small and near the zone center, it's likely not an instability. It's likely a numerical issue. If it's away from the zone center and tends to be larger, then it could be an instability. So I've looked at both, but in this case, I mean, seriously, I have zoomed in quite a bit. Like this is, if I looked at the full picture, this would look like a little bleep down here. So yeah, I would tell them to be careful with that.
Okay, and so if you run VASP or Quantum Espresso, these kind of corrections are not?
No, they're not in there yet. And I haven't published this, so I don't know if they, I don't know. The problem I have with this is that we've been able to say analytically that this thing should go to 0 and quadratically, okay? We've been able to say it for, I think Marzari has a proof for like a single layer system. We have a proof for double layer, triple layer, buckled, any kind of system, but not beyond 3 layers because the proof gets unwieldy to prove it. And so I'm sure it's general for n layers, and that when you get to bulk, I mean, as you go more and more layers, it becomes quadratic closer and closer to the zone center until it becomes linear when you get to bulk. But it's like a limit that it goes to. And so I haven't been able to prove that yet mathematically, which I'm not a good proof guy, so I may never do it. And also, we haven't been able to prove this for electrostatic interactions for like hexagonal boron nitride. I see it works, but I'm not sure that I should make it work because Born-Huang has a whole different set of equations and things. So anyway, it's kind of limited me, and I lost interest, I guess, and stepped away. But all those things. So derivative permutation and point group symmetry are enforced at the beginning for me because I don't even look at, I look at a reduced set of force constants, calculate those, and then map them out. So those are already kind of enforced already. Now, if some DFT like VASP, they'll just calculate all of them, and I think they enforce those. Acoustic sum rule I do after the fact like everyone else does. And it's the rotational invariance and Born-Huang, these two, that I enforce special afterwards. The same thing works for 1D systems. So, so here's my 1D systems here, polyethylene chain, Ba3N, and a 5,5 carbon nanotube. I don't know, just some random ones we picked out because we had the data. Anyway, that's all numerics. I kind of want to move on to a little more physics, I guess. I have 10 minutes, so I'll go quickly. So, why are those silly little modes that go imaginary important? For me, they're important because I find that they carry the majority of heat in graphene and some other systems, particularly flat 2D materials that can be important. And the reason is, so here's a bigger, so that blip will look like this here, like a little tiny blip down there. Anyway, so this is my, the quadratic acoustic out-of-plane vibration. Here are my linear modes, which have fast velocities. So people used to think that these had to be carrying all the heat. And the Gruneisen parameter, which kind of gives you a measure of how the phonons interact, the anharmonicity, nearly diverges for this guy. So they said, oh, it's got a really large Gruneisen parameter. Its velocity is going to 0, so it doesn't carry any heat. So a lot of papers came out, Ballenden, with models, including just these guys. So when we do our full approach, what we found is these guys are carrying about 70% of the heat. And I was finding scattering rates, so I look at each one of these little scattering interactions, I was finding a bunch of zeros. And it was driving me crazy, because if you find numerically 0, it's kind of telling you something. And so after the fact, we finally understood that when you look at the interatomic potential of this thing, if I take an atom on a flat sheet and I pull it up, so in the positive z direction, I see some potential landscape. When I pull it down, due to the reflection symmetry, even though I'm pulling down, I see the same potential. And so what happens, that shows up when you calculate your perturbation expansion of your potential. So what it does is the problem is that if you push it up or push it down, you pick up a minus sign in here, in the z direction, okay? So I'll say that's up and down, across the plane. So if I look at an interaction where it's say this guy is z, then I pick up a minus sign here, a minus sign here, so they cancel, and so that I can automatically satisfy this equation, okay? Now, if I have an in-plane vibration, so say this is x, and this is z, I picked up a minus sign, which means that Vz is equal to minus V minus z, okay? And And so what happens there, we're like, well, that's a problem. But what happens magically, these things go to 0. They're 0 at that because of that symmetry rule. So you can satisfy this magically. So that's why when we went to the third order, we were seeing all these zeros come out in our scattering rates. And what it really led to is the fact that this mode, when I add it to this mode, can't scatter into itself, or it can't scatter into the ZO mode. You can't have interactions like this. Otherwise, they'll be 0. They're not worth calculating anyway. And so we started getting an understanding of why these modes were giving preferential thermal transport in graphene. Is because you're restricting a lot of the phase space for scattering for these guys, and the lifetime is much higher. I mean, the same thing happens for these in-plane modes, but they're less sensitive to it because they're already in plane. So that was nice and all. We apply it, we look at the thermal conductivity versus temperature, compare this to select data. Now, some data will actually be down here, some will be higher. And this is kind of what we see. We see ZA vibrations contributing a lot. We see the in-plane vibrations not contributing very much. Notice the RTA approximation, which I didn't talk much about, but it fails for this 2D material. What I really liked about this work, though, is it gave me insights into other things, not just graphene. It let me understand, say, what happens when you couple layers together. So when I couple layers together, I get a drop in the thermal conductivity. It goes from here to here, and then kind of converges to that of graphite. And the reason I get that drop is when I couple the layer, I break that reflection symmetry. Now I push this atom down, it sees another plane of atoms. When I pull it up here, it doesn't see that other plane. So it breaks that reflection symmetry. And so you get more scattering of the ZA phonons. And lo and behold, when I look at the ZA contribution, it drops while the in-plane stays pretty flat. Nothing really happens. And so I kind of understood what was going on with layered graphene. I can understand what happens when you put graphene on a substrate. So you put graphene on a substrate, it also breaks that reflection symmetry and couples to the substrate. That's a problem too. And so you get a really large reduction in the thermal conductivity. I just remember when Li Shi had all this data, he was trying to understand it. And it was driving me crazy because I just left grad school, started a job teaching 4 classes. I was still writing my thesis, had my second baby, and he's like, I need this data. And I was like, it's 3 a.m. And I'm like, so glad I don't have to do those things anymore. He's mellowed out a lot too. That's kind of nice. When the sheets are buckled, so silicene and germanium are not flat anymore. They're kind of buckled silicon, germanium layers. That's why you get a large, they have lower thermal conductivity in graphene, or partly the reason. When I artificially apply the symmetry rule, you'll see a higher thermal conductivity. But moving away from that, my favorite was looking at the carbon nanotube. So if you look at a really, really large carbon nanotube, it's basically a graphene sheet, okay? So say you go to infinitely large nanotubes of graphene sheet. Once you start looking at smaller nanotubes, you get a curvature of the sheet. And that curvature breaks the reflection symmetry as well. So if you look at really large diameter, you go that way. And then you start going to smaller diameter, you see a reduction in the thermal conductivity. It starts to drop off. It's not super strong, because the curvature effect is not all that strong. And then it hits a minima and starts to go up again. The reason it starts to go up again is because quantization of these modes here. So you still always have these acoustic modes down here. But as you go to smaller tubes, you get less and less of these optic scattering channels. So you see this balance, this non-monotonic dependence. And I can even look at the coupling, or look at the different vibrational modes of this thing. So the out-of-tube vibrations are actually those out-of-plane vibrations in graphene. And the in-tube vibrations are the in-plane vibrations in graphene. And what I see is that these these in-tube vibrations don't change a lot, and it's those out-of-tube vibrations that are changing. Kind of gave me an understanding of what's going on in carbon nanotubes, which is fun. Twisted nanotube. Okay. So I don't have that here, but we looked at armchair zigzag and all achiral, a bunch of achiral tubes, so it was like a twisting. And they all land on basically the same curve, so thermal conductivity is not caring much about it. For me, I care about it because people in the past couldn't do calculations like this. I had to actually develop a whole formalism that used chiral operators, and the reason I'm interested in that now is because I realize it applies to 1D materials too. And it gives you these different, all the phonon polarizations have a different chiral rule, a different quasi-angular momentum. And I can use that in my scattering. So instead of having the traditional translational invariance or translational momentum and conservation, I also have to conserve this chiral angle. And I'm finding that in 1D materials like polyethylene, this BA3N system here. And it's interesting to me because that limits the kind of scattering. So 2 blue phonons have to scatter into another blue phonon to conserve this. And so that's what I found with the carbon nanotubes. But for the achiral ones, it was really hard to describe because their unit cells got large.
How about the parity?
Parity.
The parity of the
You
the
use these
number
big
of
physics
layers.
words, I don't know.
No, I mean, no. It's just like a even or odd number of layers, because this, in some cases, you have reflection symmetry and the other not.
Right,
You
sort
gave,
of.
your example is 2, this is even.
Right, so I've started to look at that in terms of this 1D system here. But like, okay, so if you have 3 layers, right? If I take the atom in this layer and I wiggle it this way versus this way, it looks different. But in the middle layer, it looks the same. So I think that comes out somehow, and I found it in this system. It drove me nuts because I applied this pseudo-angular momentum rule, and I still found zeros. And I was like, well, I took care of this. I know the physics. And what I realized is that if I have 3 N atoms along this chain vibrating, if 2 are out of plane and 1 is in plane, I also get zeros, similar to that graphene reflection rule. The problem is it's kind of hidden in there. And I think it only really showed up in this case because these were all nitrogen atoms compared to barium atoms, so there was no flavor of the barium getting mixed in there. So yeah, I did look at an MOS too, because I thought, oh, the molybdenum in there, but I don't see any zeros. I do see reduced, but yeah, I still have to flesh that out. I have 19 seconds. So I found it works in 1D chains. I found that's why the 1D chain has a higher thermal conductivity than the bulk system. Interestingly, in this system, you can intercalate the atoms. This is actually the real crystal. There's like big antimony atoms that sit in there. And what it does, it kind of pulls the chains together. And so we thought it'd have higher thermal conductivity, but it's lower than just the BA3N itself. And the reason is when you put these antimony atoms in, you're actually not only like pulling the system together, getting higher velocity phonons, but you're also providing more scattering channels. So these are like Einstein modes that are low frequency, and they're killing our phonon thermal conductivity. I was going to go back to 2D. So this is some flat boron arsenide, which I thought was kind of silly, but anyway. It had kind of the same behavior as boron arsenide. This was just some other HBN. I really wanted to get to, I guess, this, because you're always interested in the stuff you're working on now. So I was looking at molybdenum disulfide. People have done this a long time ago. There's 100 papers on it, so I was like, I'll never look at it. I don't care. But then I started looking at the papers, and it's like all the calculations are like all over the place. And these are all DFT. Well, some are empirical potentials too. You get some temperature dependencies that are different. Bulks, a little bit better, except if you bar these data points here. Bulk is kind of here. These black points and the hollow points are the single layer. They're all kind of all over the place, and it's driving me nuts. And so I did some LDA, GGA calculations, did some comparisons. And I find that if I include vacancies, which the monolayer systems, CVD grown and mechanically exfoliated, tend to have a lot of sulfur vacancies, they can actually describe the data. So there's one paper out there that kind of really looked at this a lot. I think you looked at this too, didn't you? Although I didn't get concentrations from you, I don't think. I think a different paper, we were getting the concentration of vacancies out. I can do DFT, phonon vacancy scattering. And this is the average concentration they see, and this is the range that they saw in like 30 samples or something. And if you look at the range, and you come across here, it kind of covers most of that data, barring that silly point right there, which drives me nuts. Sometimes I don't trust those experimental guys. But anyway, I was kind of happy about this. We're trying to write it up now. And if you can motivate any of your experimental colleagues to grow good samples, please do, because these are the only 3 temperature-dependent things I could find. One has a T to the -5 dependence, which can't be right. It's on a substrate, though, so maybe something weird's going on. And these are 2 suspended, but they're really flat at higher temperatures, which means you're not really seeing the phonon picture going on. Anyway, I'm sorry I took up too much time. I guess I'll go to the summary there. Summary. This picture I always like to put up because it's also unpublished work by my daughter, Eliza Lindsay. We worked on this together when she was like 3. See, I drew the straight lines. She was the one underneath, I think, doing all the phonon hop. It's probably a hopping model. And I'm like, what is this? Anyway, thank you very much.
We
No
have
more from you.
few quick questions. I have a question. So when you do a DFT calculation for the electronic part, you really know what's going wrong. So you know